for this problem, so this is from the 2023 academic year, past exam. So here, what are they saying? They're saying we have aluminium, and in this case, it has a diameter, and here the diameter is given as 3 millimeters, and it has a length, and the length here is given as 4 meters. It is used to support a mass of 50 kg. So the mass there is 50 kgs. What is the elongation of the wire? So the elongation, what does that imply? What do they want us to find? Then we're also given the Young's modulus. So here, once they start mentioning Young's modulus here, elongation, it should already point to you that this problem is coming from properties of matter. And let's try to picture the problem so that you have an idea of what is happening. So it's like you have a wire that is supported at one end, fixed. And then to the other end of this wire, we are saying it is used to support a 50 kg mass. So let's put our mass down here. Okay, so the mass here, 50 kgs. So what you have to see is that in this case, the weight of the mass is what will create a force that will be acting through our wire. When the wire feels the effect of the weight, the wire is going to elongate or become slightly longer. So probably after some time, under the influence of that weight, the length of the wire is going to change. So if initially this is what we had, let's say after some time, we observe that the wire grows in length, and then it becomes slightly longer. Let's say it goes up to that point. So we see that now when we try to check how the initial length compares with the original length, we see that the length has changed. There is this slight extension that has occurred. This is the elongation that they want us to find. Let's take it as change in x. The initial length of the wire can be taken as L0 or X0, while the new length of the wire from here, so the initial length can be taken as from here all the way up to there, while the new length of the wire can be taken from here up to that point, let's say X. So the elongation that has occurred, which is the extension in our wire, can be viewed as the new length minus the original length. So of course, we can keep this in mind just in case the problem there's a problem where they get to ask us to say, find the new length of the wire. But in the meantime, our problem is only asking us to get the elongation of the wire. So how do we get the elongation? We saw earlier that from the definition of Young's modulus, which is stress over strain, then we're going to have the expression for Young's modulus will reduce to this version, as Young's modulus is equals to the force multiplying this was the original length divided by the cross-sectional area multiplying the change in length of the material. And in some cases, as we pointed out, the elongation or the extension can be made subject to the formula. In this case, what comes here will be the Young's modulus, since this will multiply down here while the extension will multiply to go up. So when you make change in x the subject, the Young's modulus is what will show up in the denominator. Based on that, we see that from the definition of Young's modulus, we can obtain the elongation that occurs by multiplying the force acting on our wire multiplying the original length of our wire divided by the product of the cross-sectional area of the wire multiplying the Young's modulus of the wire. So we are given the original length of the wire from the problem, that is 4 meters. That is the original length of the wire. Next, the Young's modulus is already given. So from the problem, Young's modulus is 7.07, 10 to the power 10 pascals. Okay, so that is what we have there. But we have two quantities that are missing. So we have this and we have this. But how about the force? How about the area? So in some cases, they might give you the force over area. The force over area, we know to say that is just stress. So they might just give us the stress, or we can calculate it. So what is creating the force? The force is being created because of the mass. So the weight of the mass is what will create our force. In other words, we can calculate the weight of that mass, which is just mg. The mass is 10, the mass is 50, 50 kgs. We multiply the 50 by acceleration due to gravity, we take it as 9.8 meters per second squared. So all we have to do is multiply those two. So here we get 490 as the weight. So now we can view our problem as if this extends under the influence of that 490 Newton load. So we can remove the mass since its effect on the wire is just that 490 pull. Okay, now how do we calculate? So we've sorted out the force now. We now also have the force. The force 490 newtons. With the force out of the way, the only thing missing now is the cross-sectional area. So you have to understand that when calculating stress, in this case, the area that is being used is the cross-sectional area of the wire. Assuming that the wire has a circular cross-sectional area, so now it makes it easy for us to get what the area is going to be. So the cross-sectional area, we're going for that part there, while the force is acting perpendicular to that cross-sectional area like this. So not going for the surface area of the wire, but it's just the cross-sectional area to the force. So if we take the radius of the wire to be from here to there, in the problem they gave us the diameter of the wire. And the diameter was given as 3 millimeters. So this was millimeters. I don't know if that looks like a meter, but it was 3 millimeters from the problem. So from the 3 millimeters, we can get the radius. So the radius will be equal to basically half of the 3 there. We can write that as 1.5 millimeters. And then from here, we know we need that value in meters. So we can convert millimeters to meters. That will become just 10 to the power negative 3. This would be 1.5 times 10 to the power minus 3 in meters. Now we have the radius in meters. We can use it to get the area. Area of that's cross-sectional area, something circular. This is going to be pi r squared. So from here, we see that we're going to have pi multiplying the radius, which is 1.5 by 10 to the power minus 3. So in meters, so I don't have to worry about it. I know this is going to come out in meters squared. So now I can get everything since I now have my area, which is pi multiplying 1.5 by 10 to the minus 3. Of course, don't forget here I left it, but don't forget the radius is squared. So be very careful here not to forget that square. The radius has a square. Okay, so with this out of the way, we can now substitute to get our change in length. So the elongation they want, the force, we saw it's just the weight of the mass, multiplying the initial length. We saw the initial length is 4 meters. Then divided by the cross-sectional area. So that's pi 1.5 by 10 to the minus 3. Again, don't forget that square there. Then multiplying the Young's modulus. Young's modulus, we have 7.07 by 10 to the 10. Okay, so this becomes the expression that we have to simplify. So from here, because I used standard units, whatever answer we're going to get after simplifying this, it must have meters as a unit because this is length. But the answer might be a small number, seeing that I'll be dividing by 10 to the power 10. So it might be a small number. So based on that, we might want to convert it either to millimeters or to micrometers, depending on which one would be convenient. So here we end up with 0.0039, 39, so 39. So from here we can choose to write this. Can you give it to me in three sig? It will be 0.0039 what? Is it 391 or 392? 392. Okay, but this is in meters. So from here, of course, we can convert it to millimeters so that our final solution becomes 3.92 millimeters. So this becomes the elongation that will occur in the wire.